Hi, this is Tom Klupper, and we're going to continue with part 2 of learning about the Nexum circuit simulator by simulating a lossy coaxial line. And again, this is for the Microwave Engineering 1 class taught at University of Delaware. So let me start off with a challenge that we're trying to model a type of RG405 086 semi-rigid cable. And we got some data off of a data sheet here, and what we'd like to do is recreate this cable in Nexum so that we can include it into some project, let's say. So what we do is we extract from this data some key parameters. So we have the inner conductor diameter, which is 20 thousandths of an inch, outer diameter over the dielectric, which is 66 thousandths of an inch, the diameter over the jacket, which is 0.086 or 0.086. It uses PTFE, so we know the dielectric constant of PTFE is about 2.04. And then the key attenuation data is found here, and we're going to express it as attenuation at a given frequency in dBs per meter. So we have it at 1 gigahertz, 10 gigahertz, and 20 gigahertz. So we're going to take this data and we're going to recreate the equivalent attenuation characteristics and velocity propagation of this exact coax. First, we need to take a look at the attenuation equation that's used in the Nexum circuit simulator. So it's essentially attenuation in dB equals the total length, which is P, of the section of transmission line, times a factor that has to do with conductor only losses. That would be C1, and then this factor here, which deals with only dielectric losses. So there's a very old trick that you use that if you want to try to get to C1 and C2, that you would divide through or normalize this equation by P and the square root of frequency. So if you divide through by root F, then you can get a kind of map it to this term here being Y. The two square root of F's cancel, and this term here becomes B, and then this term here, C, becomes the slope M, and then the square root of F becomes our X. So with this, you have a equation of a line that you can easily pick 2 points along the attenuation curve and solve for M, which gets you C2, or B, which gets you C1. Now, a better way to do that is if you have a whole array of attenuation data, would be to square root, divide by the square root of F, and fit it to a line using linear regression. But we're going to use the data that we have right here at 1 gigahertz and at 20 gigahertz to extract for this. So the way we do that is we just do the calculations, and you'll come up with a C1 and C2 of these two numbers. So we're going to use these two numbers, C1 and C2, in the generic lossy line model called NX Coax K. And you can see here, this is a snapshot of what you actually would see in the model. You have to give it an impedance, a physical length, a dielectric constant, and then here's your attenuation characteristics. As I mentioned before in the last video, to simulate a transmission line, you need an impedance, you need some kind of time delay, which is either done through an electrical length at a frequency or a physical length at a dielectric constant, and you need some attenuation characteristics. Here it's the C1 to C2, with, again, we'll use this model right here. Another way you can do this is use the generic lossy transmission line model, the TRLK and X. Now this one's a little goofy. So you have the impedance, and you're given a physical length and a dielectric constant. But for the attenuation characteristics, it uses this thing called A, which is essentially it's the total attenuation per meter, dBs per meter, at a given frequency, F at 1 gigahertz, but only due to the conductors only. So that's, as it turns out, if you just take C1 times root F, well, root F in this case is 1, that's the C1 term that you're going to put in there. But for losses, for dielectrics, it uses tan delta, which is the loss tangent of the dielectric material. So I did not see any relationship between the C2 term and tan delta, so I just used some first order transmission line equations to derive this formula, and this works pretty well. So you can plug this in and you get a 0.000351 for the loss tangent to put into this model. Now, of course, mu r is the relative permeability, and of course that would be 1, and there's no DC connectivity term. And for right now, we're going to use the non-causal model, which we can discuss later why, but we're just going to set it up this way. And then finally, if you want to use a different model, they have something called the NX Coax P, which is a physical lossy line coax model. Now this one uses actual parameters. So you would give it an ID, an OD, which we got from our data, a physical length, a Dodge constant. Here's our tan delta. But for conductor losses, it uses an estimate of the conductor resistivity in microohm centimeters. To get this, again, there's no equation, so I had to derive this. And you'd plug in the C1 term, your nominal impedance, your inner radius in millimeters, and then down here, again, the impedance and the root K term. You plug all those in, you get a estimate for RB that will recreate the insertion loss. Now, one thing to kind of note is if you know that the loss tangent of PTFE is more like 0.00024 and the conductivity for copper is more like 1.7. You may ask, well, why are these numbers higher? Well, the reason is because when a company gives you the nominal attenuation curves, let's say you go back here, they're including things like maybe some slight ripple due to reflections, etc. So these are going to be padded a little bit high for attenuation. These aren't going to be the pure attenuation of just the transmission line. So they're going to be a little bit higher, which is why these numbers are higher as well. And then finally, just a quick look at electrical length. If you're given a P length in meters for the section of transmission line and a Dodge constant K, the electrical length in nanoseconds is just this formula here, times P times the square root of K. That'll give you electrical length in nanoseconds. And then for electrical length in degrees, you could convert it using this formula here. All right, so let's go ahead and jump into the software and do these simulations. Okay, so we're going to create a new circuit netlist. I mean a new circuit schematic. And we're going to say OK. And first thing we're going to do is drop a couple of ports as we have done in the past. The space bar, I'm going to zoom in. And the first one we're going to look at is the ideal distributed, nope, we're not. We're going to look at the coax cable one. So the coax cable, the NX coax K, I can never find these things. There it is. There it is, right there. Coax K. Double click on it, bring it over here and hit the space bar. You're going to connect them up. And we're going to double click on this guy and we're going to put in the numbers. So we have a 50 ohm cable. We want the cable to be 1 meter. Now watch what I do when I click and type in 1 meter. It changes the units to meters, which is really kind of nice. Dodge constant, we're going to say 2.04 for PTFE. For C1, we're going to use the numbers that we had calculated, which is 0.676139. That's for our RG405086 semi-rigid. And then the C2 term, the dielectric loss term, is 0.045661, and keep the model W. Okay, so that should be enough information for us to reproduce our coax transmission line. And again, these are probably default to 50 ohms, but it doesn't hurt to check. All right, so let's go ahead and do a quick simulation. We have our ports, analysis, right click and select a Nexum linear circuit simulator. We're going to edit this guy. I'm going to do a linear step. Let's just go from 0.5 gigahertz to 20 gigahertz, stepping by 0.5 gigahertz. Okay, so pretty coarse, but we're only going to look at attenuation. I am going to click on enable group delay calculations at 0.1% because we're going to take a look at the group delay this time. Say OK. Now we have this. I'm going to right click on analysis and say analyze or press F10. And very quickly you can see that it should do the analysis pretty lickety split. There we go. Okay, we go down here to results. I'm going to right click, create a standard report, rectangular plot. I'm just going to look at S21 in this case in dBs. We just want to look at what comes from from port 1 to port 2. Just insertion loss is all we're doing. Say new report, say close. Okay, so here we have our trace. So I'm going to right click and say marker. Let's place markers where we have that data, which should be 1 gigahertz, 10 gigahertz, and 20 gigahertz. Right click and marker mode, and then drag this down here. I think I'd mentioned before, I like to change the visibility of the legend and just drop that legend because it kind of gets in the way. Okay, so what do we have? We have 0.7218, and if you remember from our data, we had, let's see if I can call it, what's it, 0.7218. Let me just drag this out of the way. And 0.7218. Okay, again, it's 1 meter long. This is 2.59, it says the 2.6, so it's a little bit lower than the actual nominal data, but at 20 gigahertz it's 3.937, 3.937. So it does a pretty good job. Our model here does a pretty good job of estimating the actual insertion loss of the RG480-405. I'm going to click on results. I'm going to add another plot. So create a standard form rectangular plot. I'm going to go down here to group delay, again S21, say new report, close. I am going to blow this up because for some reason it likes to scale it like crazy. So let's make the minimum, I don't know, I'll just say 4.7, and we'll make the maximum 4.8 nanoseconds, and we'll change this at like 0.1 just so we can take a look. And sure enough, right click marker, just let's say, I don't know, we can do it at 1 gigahertz, let's just say. We get 4.7643, which again, if you do the calculation of the, using that formula from before, which is right here, toward the very end, you could plug in that number, 1 meter, square root of 2.04, and you'll get that electrical length. Okay, let's take a look at, I'm going to end the marker mode. Oh, let's go ahead. All right, let's try the other circuit. I'm going to zoom out here. And the next one we're going to look at is the generic transmission line of physical length. This is the right one, yep. So I'm going to double click him. Click space bar. Let's add 2 more ports. And I'm only doing this so we can simultaneously look at the data at the same time. So this one will be between port 3 and port 4. Let's double click and we're going to put in the data for this. 50 ohms, 1 meter, K of 2.04. Again, this is the attenuation due to just the conductor, as I mentioned. Move this out so we kind of see that a little bit. So that would be the C1 term, 0.676139 at 1 gigahertz. So that's just due to the conductor. We calculated tan delta using that little formula I came up with, 3.51, 1, 1, and we're going to use non-causal. Okay, so this should create the same attenuation using this different model. This is just a generic transmission line model where we specified the attenuation due to the conductor and the dielectric in a slightly different way. Okay, we're going to keep the same analysis frequency. The right click and say analyze, and I'm going to double click down here on port 1 once it's done. I'm going to double click on this and say let's add another one. So that was 1, 2, 3, 4. So we're going to look from 4 to 3. I'm going to click that guy there. We're going to add the trace. So as you can see, they overlay each other. So they give us the exact same attenuation characteristics, even though they are different models. So let's go down here and add 4.3 to our group delay. So there's our delay through the line. Again, the exact same delay. All right, so that just shows that we've achieved the same objective using different models. Let's add now the physical coax model, which is NX coax P, NX coax P. I'm going to add that guy there. Press the space bar, add 2 more ports. Space bar, we're connecting them together. And we're going to put in the data here. So we said that this one is 0.0221 inches, and the outer diameter is 0.066 inches. The physical length is 1 meter. And notice as I'm typing this in how the units change to what I typed it in. So I really love that feature. 2.04 for dielectric constant, tangent 0.000351, and again for the conductor resistivity it is 2.322. And again, there's no real description. I had to kind of just derive what these are, relationships to C1 and C2. If anybody's interested in how I derived it, let me know and I'll share that with you. Okay, so we've just fully characterized or fully populated this element. Say OK. Let's go ahead and redo our analysis. Press F10. And we're going to go down here and add this guy, which is 1, 2, 3, 4, 5, 6. So that would be 6, 5, right? Port 6, 5. And again, it's the same attenuation. So all 3 elements are representing the attenuation the same. And let's look at group delay, because those are really the only 2 ones that we care about. 6, 5, add trace. Okay. So port 1, so that's model 1, model 2, and model 3 all give us the same, generally the same results. Okay? Great. Now I'm going to do one other thing. So that just shows you that I can recreate the attenuation curves of that cable, and now I can include that cable in anything else and have it be representative of that particular RG semi-rigid. Let's do something else which is kind of fun. I'm going to add another project. So we're going to add go to desktop, go to projects. I'm going to add a Q2D, and we're going to try to add a piece of coax by actually doing a 2D model. It's thinking, it's thinking. Okay, so here we're going to draw the cross section of a coax. Now this takes a few steps, so bear with me and hopefully you'll pick it up on the way. So I'm going to draw my cross section. Okay, first I'm going to click on the circle, but go to the center. I'm going to draw out and then click out here. What will happen is you'll get a box when you double click on it, of course. So we have, what do we have here? We have, these are sheets. It defaults to copper. This is called circle 1, and I've created a circle. I'm going to double click on this, and for the radius, this is the outer, I'm going to make this the outer jacket. So let's make this one called D. I called it DJ. I think I did DJ over 2 is the radius. Now I haven't defined DJ over 2 yet, but look what happens when I say, hey, it's DJ over 2. When I press return, it goes, well, what's DJ? Oh, DJ is 0.086 inches. When I click on this, notice it changed to inches, and it divided that by 2 because it's a radius. Okay, say apply. All right, let's add another circle, and I'm going to click here and just kind of draw it out arbitrarily. It doesn't really matter. I'm going to double click on this, and this one I'm going to call DO over 2. DO is going to be the outer diameter, as we mentioned, and that was 0.066 inches. See how it divided it by 2. Say apply. Okay, now what I'm going to do is I'm going to click on circle 1, press the control key, press on circle 2. So they're both highlighted. I'm going to go up to circle 1, right click, and say edit Boolean Subtract. and it's taking circle 1, the outer one, and it's going to subtract circle 2 from it and create a new part. Okay, so our new part has the jacket minus the outer diameter, and it's defined as copper. Okay, let's see. I'm going to change this. So I'm going to see the circle. I click on this. Let's change this name to DO. And I'm going to click the material. By default, I can either make it copper or vacuum. Well, I'm going to make it my own special material, and you'll see why in a second. If I click Edit, and I'm going to say Add Material, I'm going to call this Modified Copper. Why not? And it's just going to have a bulk connectivity. Now, here's what I'm going to do. I need my calculator. So we're going to take the connectivity that we used before in our transmission line models, which was 2.322 e to the -8, because it's micro ohm centimeters. And that is the resistivity, right? And if I hit inverse, I should get the conductivity, the bulk conductivity in Siemens per meter. And that number would be, when I did it, it would be 43,066,322. Okay, so this is the same level of copper conductivity or resistivity, depending on how we specified it, as we had before. And that's all we're going to do. We give it a name. I'm just giving it a bulk conductivity of the same value that we used in our copper losses or conductor losses from before. And we say OK. So now this DO is defined by mod copper. Great. I'm going to click on this and I'm going to add another circle. Just click on here, doesn't matter. See, it always defaults to copper. I'm going to double click on this one and I am going to make this radius DO over 2. It already knows what DO is over 2, and you'll see why I'm doing that in a second. Say apply. But I'm going to click on this circle 3. I'm going to change the name of this to dielectric. Okay, and I'm going to change the material. I'm going to say edit. I'm going to say create a new material. I'm going to call this one PTFE. And I'm going to say it has a relative permittivity of 2.04. A dielectric loss tangent of 0.000351, I believe it was. And that's it. So no permeability, no conductivity, no magnetic properties, just decay and loss tangent. Say OK and say OK. So now notice that the circle called dielectric is now made of PTFE. I am going to change one other thing. Let's change the color of this. So it says color. I'm going to click down here. Let's just make it yellow, just so it's different. And the transparency, I'm going to make that kind of transparent. Make it like a 0.8. So it's kind of a, wow, that's pretty transparent. Maybe not that transparent. Let's make it 0.5. So you can just kind of see it, but it's transparent. All right, one more circle, and that will be the center conductor. I'm going to click on here and draw another circle. We're going to call this one DI. I'm going to change this one to our mod copper. I'm going to change its color to, I don't know, let's set something copperish like that. Maybe I can even click on this guy and change this to a bit of a copper color if I like. All right, here's our coax. We have a center conductor DI that has, well, actually we don't have to do that. Why? Because if I click on this, remember I talked about this properties window, you can access it all the way down here. Of course, why does it show millimeters? Because it's our default unit. If I double click on this, you can see that it defaults to the 0.316. But more importantly, I can click on the project and it shows you, here's the two variables I have. Why isn't this? Oh, I haven't changed it yet. Ha! All right, this is DI over 2. Oh, that's funny. DI over 2, and it's saying, hey, what's DI? 0.0201 inches. Okay. That's better. See, about 10 mils. Okay. Now when we click on this, we see our variables, DJ, DO, and DI in inches. Okay, everything's properly defined now. We have DI as a center conductor, DO is the outer, and the dielectric is PTFE. Great. So what we need to do now is go to Conductors, and all we've done is drawn the geometry right now. What we need to do is actually assign the conductors to something. So if I would left click on Conductors, right click and say Auto Assign Signals, you'll see that it'll put, it knows to add, oh, this is going to be one signal trace, and this is the other signal trace. However, we like one of these to be ground reference. Remember, we always talked about transmission lines having a ground reference. I'm going to click on DO, right click, and say toggle to reference ground. So now DO is the reference ground, DI is a signal ground. So now I know particularly what we have here. Last thing we're going to do is click on analysis. I'm going to say right click, add solution setup. Okay, so I'm going to do the solution at 20 gigahertz. I'm going to change the number of passes it needs to 20 for each of these matrices. The precision to 0.1%. And essentially what it's going to do is it's going to iterate at least 20 times or no more than 20 times to make sure that the capacitance matrices are within 0.1% error of the previous, and then the impedance, resistance, inductance matrices are also within the same amount. So it means my solution should have an accuracy of 0.1%. And you can click on the HP analysis, click on edit to make sure that, oh, I'm using only 3 cores. You can change the number of cores that your solution uses. I'm going to use 4. All right, so we've changed the cores, we've updated this page. You don't have to change the rest of them. I would leave them as defaults. The CG, the RL, express defaults. I would not change these. I would only modify the general setup in your solution. Okay, so now we have an analysis, but now we click on setup, right click, and we go add a frequency sweep. So what I'm going to do is I'm going to delete these because these have multiple frequency sweeps. So I'm only going to do one linear step, and I'm going to go 0.5 gigahertz. I'm going to have it match the one we did before in the linear setup, and the step size is 0.5 gigahertz. Okay, 40 points. You don't have to change anything else. All we're doing is going from 0.5 to 20 gigahertz to 0.5 steps. Okay. Now we're all set, ready to do a simulation. But before we do, I just wanted to show you something. Let's go to setup. Let's go to analysis. Click, right click, and say generate mesh. Oh, I guess we've got to save it first. Of course we do. Getting started. We're going to call this starter part 2. This shouldn't take too long. Now I may have to change a couple of settings. Let me just, you know what, I'll tell you what, I'm not sure how long it's I'm going to pause it for right now, and then when it's done, I'll unpause it. Oh, I guess that was quick. Okay, let me do one thing. I'm going to click on this project, the 2D extractor project. I'm going to right click, come down here to solution type. Nope, that's not what I'm doing. Click on this down to design settings and go over here to Lossy dielectrics. I'm going to turn off automatically use causal materials just for right now. I'm going to then click on the PTFE dielectric. That's the center thing. Right click and say plot mesh. And you'll see why. Okay, so we generated the mesh, and this shows you the initial mesh condition. So if you don't like it, you can always, there's things you can do to change that. We won't go into that right now. But I think we're all ready to do the analysis. So I'm going to click on analysis, right click. Oh, nope. What we're going to do first is 2D extractor and do validation check. So these all have to have green check boxes. I knew they would, but let's go ahead and do that. All right, now we can go ahead and do this. Click on analysis, right click, analyze all. and you'll start seeing in the lower right hand corner it's doing its analysis. Now this will take several minutes, so I am going to pause the video until it's done. But take a look at the initial mesh condition compared to when it's all done. Okay, it's done. That took several minutes, but you can see the final mesh is a lot finer. So we're going to go down here to results, right click and say create a matrix report, and let's just take a look at the characteristic impedance. And you can see that that's about 50 ohms, and it has this dispersive relationship here because of the conductor losses. So here's what we're going to do. Here's the fun thing. If I let me just close this. I'm going to close all the. So I'm going to click on this project, the 2D extractor project. I'm going to press Control C, click on the control circuit, and press Control V. And what it should do, if I did it right, is it should add this to the circuit. And sure enough, here is a co-simulation where we've added the 2D extractor output to the input of the Nexum circuit simulation. So now all we got to do is add some ports to the in. Remember we defined the input references as the outer conductor. So we're going to put a couple grounds. We're going to connect them together. So connect port 7 and port 8 to the outputs. Connect the input to references to ground. And everything's set up. It's from port 7 to port 8. So I'm going to click on analysis and go ahead and say analyze. And this will not only analyze the 3 linear circuit simulation transmission line elements, but it should include this as well. So now when we go to S parameters, or S parameter plot, we can then include ports 7 and 8. So that would be S8, 7. It should be right there. Add that. Oh, I forgot to do something. Let me go back. Double click on this. I forgot to find the length. It said 10 millimeters. No, we want 1 meter. So it's doing a 1 meter. It's taking the parameters that it solved in the 2D extractor and it'll make it 1 meter. So now when we go through and do the analysis, it should give us the proper loss characteristics for a 1 meter version of that coax. And there we go. So what we mentioned that the first 3 elements give you the exact same attenuation, but this guy has a little bit higher attenuation. That's this this brown curve here. Partly has to do with the fact that it's modeling the conductors differently. So we can go to the group delay plot, and you'll see why. Double click this. I'm going to group delay 8, 7, add the trace, and sure enough you can see that it's a little bit longer and there's more dispersion. So this is going to give you a more true representation because it's an actual field simulation. So these are circuit simulators. This one's including a 2D field simulation that you've just defined right here. Okay, I'm not going to go too much more than this because I think it's enough for today, and we will catch you in the next section. Thanks a lot.